behave in an ideal way when the pressure is low and the temperature is high. In this illustration, on the left, you see what's supposed to represent a gas at low pressure. And at low pressure, these other gas particles are far away from this darker blue particle. Coulomb's law tells us that the farther apart the particles are, the weaker the attraction. And so ideal gas, according to kinetic molecular theory, there are no intermolecular attractions because the particles are so far apart. And so this darker blue particle here will not be slowed down at all or influenced at all in its motion by these other particles. If those particles are there, it kind of slows this one down and it does not collide with the wall of the container as hard, and therefore the pressure will be lower. That would be for a real gas, right? So over here on the right, we're going to have gas that behaves in a little more real fashion. We are at high pressure. These particles here are much closer. Again, Coulomb's law tells us that if they're closer, the attractive forces are going to be greater. And so they will influence the motion of that particle much more, thereby reducing the speed with which it collides with the wall of the container. And if that speed is reduced, then the real pressure will be less than the ideal pressure. Or I sometimes like to call this the measured pressure will be less than the calculated pressure. Because by calculated, I mean using PV equals nRT, right? Using the ideal gas law equation. Now, one other aspect here, as we look at real versus ideal gases, another assumption we make is that the particles don't actually take up any space. And so all of these gas particles, we are assuming or pretending that they don't actually occupy any space. And so we assume that if this is a 2-liter container, we would then say the volume of the gas is 2 liters. Well, in reality, the volume of the gas is equal to 2 liters minus the actual volume or the amount of space that the particles take up. And so for an ideal gas, that is equal to 0. We can't assume that's true under high pressure. Let me back up. We assume that's true at low pressure. And typically at low pressure, we mean high volume. Because in high volume, the volume of the particles is so small compared to the container, right? So this is 2 liters minus some very, very small number is close enough to 2 liters for us to call it 2 liters. However, if the volume is small and therefore high pressure, then, and let's pretend that the container is now this big, just the red in the bottom left-hand corner of this diagram. Well, now the space that those particles actually take up is rather significant compared to the overall volume of the container. And so now, if I take V is now, 0.2 liters minus the volume of particles, well, now suddenly this is a larger percentage of the container. And we now have to consider this because the amount of space that they have free to move is very small compared to the lower pressure scenario. So if we take a look at the van der Waals equation here, it corrects for both the intermolecular forces and the volume of the particles. Now, this is an oversimplified version of this. X and Y are a little more complex than that, but I just want to leave it as simple as I can. So X corrects for the intermolecular forces, and Y corrects for the fact that the particles actually do take up some space. And so, as we kind of break this down a little bit, we see that the real volume minus the correction factor is going to give us the ideal volume. Or if we rearrange that, then the real volume is the ideal volume plus the correction factor. Same thing is true with pressure. And so the real pressure is always going to be less than the ideal pressure, and the real volume will always be greater than the ideal volume. Perhaps it would be useful to simplify this even a little more. If we take our pressure and ignore the correction unit for pressure and just write our equation this way. When we solve this equation for VR, the real volume, we get nRT over P plus Y. So the real volume is going to be larger than what is predicted by the ideal gas law equation. If we do the same thing this time, just leaving the pressure correction in there, which is plus X times V equals nRT, and then we solve this for PR, we get nRT over V minus X, and the real pressure is less than what is predicted by the ideal gas equation. I hope this was helpful. I hope this helped straighten out some of the complications with thinking about real gases versus ideal gases.